Hi guys, welcome back. Chapter 12, Section 2 today. Kind of a complicated section today, I'm not going to lie. You really need to use your imagination and relate the stuff we're talking about today to visual things. It's hard to visualize electricity, and I'm a very visual learner. I know most of you are as well. So it helps me to visualize hoses, water, things that we can actually see. Your book does a really good job of laying out some of those illustrations to compare as well, okay? But stick with me. All right, so we're talking about something known as voltage today. We have to kind of back up. Voltage is what the measurement is, but let's back up to what it's measuring. Electricity, or these electric charges, are similar to physical things, okay? And they have potential energy. Okay, so just like when you raise a ball up higher, it has more potential, more gravitational potential energy. When you have a stronger electric field, it has more potential electric energy. And we refer to that as electric potential. Okay, and what that means is that the stronger the fields, once they get into a certain range, they'll interact with each other. Okay. And we're not going to get into what changes the force of those fields. That's way too complicated for our levels. Okay, so that electric potential, that difference between those fields is known as the potential difference. Okay, and that's measured in volts. And voltage is just another name for that potential difference between those electric fields. But that difference, that potential energy between those two electric fields, is what allows that electric current to flow in the first place, okay? So we've talked about current before. Voltage is just another name for current, okay? And that's what allows the electricity to flow through a circuit, okay? Not too bad, right? What are our voltage sources, all right? Well, the voltage source is what actually creates that potential difference in a circuit, okay? And commonly they're batteries and generators. Most of what we plug things in for uses electricity that's coming from huge power plants, and they use generators. But a lot of our stuff, our cell phones even, use batteries, okay? So think of a battery as lifting the charge, okay? So we lifted our marbles for our skate parks to give it that initial potential energy. A battery is lifting the charge to create that potential difference, okay? And a battery really is nothing more than a chemical reaction. The lift, so to speak, is an ongoing chemical reaction within the battery. And if you notice, these four batteries right here all have the same voltage. They're all 1.5 voltage batteries. The reason they have different sizes is for convenience. You wouldn't want to put this big D-cell battery in your remote control, right? You want something kind of small. But the bigger the battery, the more material there is in it for that chemical reaction to occur. Those batteries will last longer. But if you think about items that use these kind of batteries, they don't use very many. Maybe 2, maybe up to 4. I don't think many things even use C batteries anymore. But D batteries go in things like flashlights, or do they even use them in portable radios anymore? I don't know. Most of that stuff has rechargeable capability now. But a lot of the objects that require those larger batteries require a lot of them because they actually require a lot of electricity to work. Anyway, I have a video for you guys to watch, a TED Ed video for you to watch that talks about that chemical reaction inside of the batteries. Just kind of for your information to further your curiosity, because I know you're dying to know. All right, let's also talk about resistance. We've talked about it before. Resistance is just that opposition to flow, okay? And that should make sense to you. If I am resisting you guys from walking down the hall, I'm making it more difficult for you to move, right? Same thing with electricity, okay? And it's measured in these things called ohms. We're going to talk about that a little bit more and use that funky little Greek letter as the label when we talk about resistance, okay? Again, the higher the resistance, the lower the current, okay? Even if the voltage is the same. So even if you have the same source of electricity, if there's higher resistance, you're going to slow down that current, or you're going to prevent that current from getting through as well. Sometimes that's on purpose, okay? Remember, our resistors, like our light bulbs, cause resistance, but that's kind of the point. But oftentimes we talk about the wires that we use, okay? You want to create the easiest path for the electricity for things to be efficient. And the wire selection is important. Think of hoses. If I had a really, really, really long hose, like a 100-foot hose, the water would flow through it, but there's going to be a lot more friction, okay, than a short little 10-foot hose. A longer wire has more resistance than a short wire. Again, back to a hose. If I'm trying to get water through a little tiny straw, it's going to resist that. It's going to take a long time to get the water through that little hose versus like a big fire hose. The water's just going to gush out of that fire hose, okay? Same with wires. A thinner wire has more resistance than a thicker wire. It just slows that current because there's not as much material for it to go through, okay? All right, well, now we can put all these things together, all right? Resistance is equal to voltage divided by current. And yes, you're going to have to do some math, okay? This is known as Ohm's law. It's named after some dude named Ohm. We're not going to get into him very much, okay? Resistance, again, is measured in ohms, and you use that little funky, it looks like a little fat dude's legs, right? Like he's got his little hat on. I guess he'd have some arms in there too. Hi. Anyway, sorry. Moving on. My ADD is still working strong. Even stronger right now. Voltage is measured in volts, and we just use a V for that. And you can use an instrument known as a voltmeter for that. Some of you guys might have one in your garage even. You can ask your parents about that. And then current is measured in amps, and we can just use an A or a lowercase amp, A-M-P as a label for current, okay? Now, I've got this kind of fun device for you here. You notice that we've got this triangle, okay? And we've got V for volts up top. We've got I, which is actually the current, okay? And then R is our resistance, okay? Now the reason they use the letter I is because the letter C already has a definition to it. The letter C in science is the speed of light. It's a constant, so we can't just stick a C in there. But anyway, what this little triangle does is it allows you to figure out the equation for whatever piece is missing, okay? So if voltage is missing, like up here, you've got these two next to each other, and it means you multiply them together. So if you're given the current and the resistance, you would multiply them together, and that would give you the voltage, okay? If the current is missing, you've got the V over the R. Well, that's a division problem. You divide, that's a check mark, not a V. The voltage divided by the resistance would give you the current. And then last, if the resistance is missing, it's another division problem. You've got the volts being divided by the amps, divided by the current, okay? So if you guys look at page 383, there's some practice problems there, okay? First one says, what is the resistance of a headlight connected to a 12-volt battery with a current of 0.4 amps, okay? So we're looking for the resistance, so we're going to use that equation right there, okay? And we're going to divide volts by amps. So it's simply going to be 12 divided by 0.4, and that is going to give us 30 ohms. We use that funky little label for resistance, okay? I need you guys to look at those practice problems. I also need you to look at the Sharpen Your Skills problems on page 382. And you guys are going to need to do those as an assignment, okay? I'll write that up for you in Edmodo, all right? And that is Ohm's Law. See you guys later.